Good evening, everyone. This is Bhargav Joshi, and welcome to the course on Indian astronomy. Today we are going to conduct a lecture on instruments used in Indian astronomy. This is a course organized by Bhandarkar Institute in association with Jyotirvidya Parisanstha. And today we are going to conduct a talk on yantras, which are discussed in Indian astronomy. So, before getting into the instruments or the yantras, let us try to understand what exactly is a siddhanta, because all the instruments that we are going to discuss today are actually mentioned in various siddhantas. And siddhantas are written in the siddhanta period. So, there is a Vedic period, and after that, we have the siddhanta period. So, a siddhanta consists of two sections. The first section is called as Graha Ganita Adhyay, which is a chapter or a section dedicated to the mean motion of the planets. In Graha Ganita Adhyay, there are again three parts. The first one is called as Madhyama Adhyay, which is a chapter which deals with the mean motion of the planets. Then we have Spashta Adhyay, which is a chapter which deals with the true motion of the planets. And finally, we have the Tri Prashna Adhyay, which is a chapter dedicated to the questions like direction, place, and time. The second section of any Siddhanta is called as Gola Adhyay. So it is related to spherics, the spherical trigonometry. And every Gola Adhyay in every Siddhanta consists of a Yantra Adhyay. So all the instruments that are used for the observation are mentioned in Yantra Adhyay. So there are various Siddhantas which I have considered. So let us try to take a look at the primary sources and references which I have used for today's talk. So these are some of the primary sources and references. Now the period which I have considered is starting from Aryabhata, so around 499 AD, and Lalla and Shripati, so between 12th to 14th century AD, from 499 to 14th century. So these are all the texts in that time period. So the first one is Aryabhatiya and Aryabhata Siddhanta. So it was, of course, as the name suggests, written by Aryabhata, and the translation of this text was done by K.S. Shukla. So K.S. Shukla has done many translations of many of our ancient Indian texts, out of which this is the one. So this is what we are going to refer today, the translated version of K.S. Shukla. The second one is Pancha Siddhantika. So as the name suggests, there are 5 Siddhantas, Pancha. So out of these Pancha Siddhantika, 3 of them are of the Indian origin, and 2 of them are a translation of the foreign works. So out of these 5 in Pancha Siddhantika, the first one is Surya Siddhanta, the next one is Vasishta Siddhanta, and the third one is Paitamaha Siddhanta. After that, the remaining 2 are Romaka Siddhanta, which is a translation of the astronomy of Romans into Sanskrit, and finally we have Paulasha Siddhanta, which is a translation of the work of Paul of Alexandria into Sanskrit. So this compilation of the astronomical canons was done by Varahamira. So he's a notable figure in Indian astronomy, and he did many of the work in ancient Indian astronomy, methods of observation, and there is an entire chapter, the chapter 14th of Pancha Siddhantika, called as Chedyaka Yantrani. So it consists of all the instruments which Varahamira has used for the observation. And the translation of this text was done by Thibaut and Vivedi, and that is what we are going to refer today. The next is Mahabhaskariya. So this was written by Bhaskara I, not to be confused with Bhaskara II. Bhaskara I has written a commentary on Aryabhatiya in the form of Mahabhaskariya and Laghu Bhaskariya. And they are again translated by K.S. Shukla, and that translation we are going to refer today. Then we have Brahmasputa Siddhanta and Khandakhadyaka. So these two are written by an astronomer and mathematician called as Brahmagupta. So Brahmagupta was again a notable astronomer and as well as mathematician. He has devised various methods for the observation of astronomy or the observation of planets and motion of planets. So out of which Khandakhadyaka is considered to be his Karna work, which means it is a derivation of something that has been proposed before. So in Khandakhadyaka, it was initially translated by Beena Chatterjee, and then it was later translated by K.S. Shukla again, and those 2 translations have been referred today. So those 2 translations are actually based on the commentary of another astronomer called as Bhattotpal. So that is what we are going to take into consideration. Then we have the 6th number of Shishyadi Vruddhidha Tantra by Lalla. So Lalla was yet another astronomer and mathematician. I'm not sure about the time period exactly because this text is not really well documented. So all we know about this text, Shishyadi Vruddhidha Tantra, comes from the commentaries which have been written by Bhaskara II and Mallikarjuna. So both of them are mathematicians, and from their commentaries we have certain well documented records about Shishyadi Vruddhidha Tantra, and the translation again was done by R.S. Shukla. Then we have Vateshwara Siddhanta written by Vateshwara and the translated version by K. Shukla. And then we have modern Surya Siddhanta. So try to take a note of it. It is modern Surya Siddhanta. So it has been observed that the Surya Siddhanta has been edited over the course of centuries. So this is not the first version of Surya Siddhanta. This is the modern version of Surya Siddhanta, which has been updated. You can say the last update to this text occurred during the time of Varahamira. So this text is the modern version of Surya Siddhanta, and this was translated by Bapudev Shastri as well as Burgess, Ebenezer Burgess, and that translation is referred today as the text for Surya Siddhanta. Then we have Siddhanta Shekhara, written by Shripati. Now again, Siddhanta Shekhara has been translated later on, and K. Shukla did most of the work along with Beena Chatterjee. And then we have Siddhanta Shiromani finally. So this is a really popular text written by Bhaskara too. And Siddhanta Shiromani has again two sections. All of these Siddhantas have two sections, out of which the Graha Ganita Adhyay of Siddhanta Shiromani has been translated by Arka Somyaji, and the Gola Adhyay has been translated by Lancelot Wilkinson and Bapudev Shastri. So there was a necessity to to give an introduction of all these names as well as the names of Siddhantas, and to give you a basic idea about how the Siddhanta works. So this was necessary because you are going to encounter these names in the following PPT, the names of the astronomers as well as their Siddhantas. So I guess with this prerequisite knowledge acquired, we can proceed with our first instrument. So instruments are referred to as yantras. So let's try to take a look at the first yantra. So if you see the list, I have presented a list of yantras that I have considered. So the first one is of course Shankhu yantra, which is a gnomon. So this has been predominantly used in ancient India. The second is Chaya yantra, which is a shadow instrument. And then the one which is again predominantly used is the water clock or clepsydra. So you can see Ghatika Patra. So Ghatika Patra is used even today in wedding ceremonies and threading ceremonies. And then of course we had the Gola or the armillary sphere. So regarding armillary sphere will be covered in Graha Ganita lecture of Shri Deepak Joshi. I will just be mentioning about this yantra. The rest is a list of the yantras which we are going to discuss today. These are the miscellaneous yantras. But these which I mentioned right now are kind of predominantly used in India from the ancient times. So the first one is Shankhu yantra, the gnomon. So there is a vertical gnomon and there is a horizontal type of gnomon. And we are going to discuss both of them. So the first one, Shankhu yantra. So this was actually proposed by Aryabhatta in his text Aryabhatiya. So if you can see on the screen, there are three types of gnomon that have been mentioned. The first type is a cylindrical gnomon. So gnomon is basically an object exactly like this. It is cylindrical. It has a diameter of 12 angula and it has a length. It has a diameter of 2 angulas and it has a length of 12 angulas. Okay. Now the thing is, we should be familiar with this unit, angula. So angula is nothing but the breadth of your finger. So many of the texts consider this breadth as the thumb, but many of the other texts consider this breadth as that of the anamika. So these 5 fingers have names. So this is Tarjani, Madhyama, Anamika, Kanishtha and Angushtha. So there are variations in the unit of angula. So you might wonder why use a unit which is varying with time. So the thing is, for every Siddhanta, this unit has been predefined in the introduction, and that unit and the quantity stays constant for the entire Siddhanta. So all the instruments and observations that are recorded in that Siddhanta are predefined and they are assumed to be correct, and rather not assumed, they are correct. So the first one is cylindrical gnomon proposed by Aryabhatta. The second, as you can see, is a conical gnomon. So this conical gnomon is constructed in such a way that the base diameter is 2 angula and again the height is 12 angulas. So mind you, it is not the slant height, it is the perpendicular height, okay, height of the cone. So that is 12 angula. Now Aryabhatta describes a method to ascertain the verticality of the gnomon. So what you have to do is make holes below the top of the gnomon and above the bottom. So you can see there are two holes that have been driven. Inside these two holes, you have to insert a needle horizontally inside the holes. And then you have to suspend a string or maybe a stick to both these needles. So that will actually ascertain the verticality of the gnomon. So we cannot compromise with the verticality. If the gnomon is slightly tilted, it will have an effect on the shadow and our observations will be inaccurate. So it is necessary that the verticality is maintained. Finally, the third one is more of a rod. It is also cylindrical, but it is more of a rod. Its diameter is comparatively negligible as considered to the length. And again, the length of the gnomon is 12 angulas. So these three types of Shankhu Yantra were proposed by Aryabhatta himself. But the thing is, there have been certain additions on Aryabhatta's Shankhu Yantra. So this was a Shankhu Yantra reconstructed by Bhaskara. So in the following slides, you are going to see the shlokas, and below them are the translations. So you do not need to read the shlokas right now or even the translation. They are just for your reference. I will be explaining the figures which are there on the right hand side or on the left hand side. So now this is a reconstruction proposed by Bhaskara too. So on the right side of the image, you are going to see a cylindrical gnomon, and on top of it, there is a needle which has been mounted. So that needle is in such a way that the height of the needle is greater than the radius of the gnomon below it. And that is the rule described by Bhaskara 1. So this was actually to improve the precision or maybe to achieve accuracy in observation. So this was actually a modification which was proposed by Bhaskara 1 in his commentary Mahabhaskariya. Then we have another modification to it which was proposed by Brahmagupta, as you can see. So this is a conical gnomon which we saw earlier, the type 2 gnomon. And this conical gnomon is in such a way that you have to suspend two plumb lines. So in the earlier slide there was a single plumb line, and this has two plumb lines which have been, you can say, suspended. And again there are two nails which are driven horizontally. So this gnomon ensures that the orientation is not just vertically accurate but also horizontally. So that is exactly perpendicular to the ground, and that is what the gnomon achieves: verticality and horizontality and accuracy in both of these axes. So this is like a general view. I'm not sure if you're able to see the screen quite clearly, but if you try to see it, I have created a tabular format of all the additions and the types of gnomon. So the first three are proposed by Aryabhatta. You can see the diameter, the height, and the material. So the material referred to is of timber, and you can see the diameter is 2 angulas and height is 12 angulas. Then we have Bhaskara 1's addition. So I just described the third type of gnomon described by Bhaskara 1. I did not discuss the first two types because there is not enough data about them in his own text. It is kind of, you can say there is a discrepancy in the data. Now regarding the third type, I've already mentioned the material to be used is again timber. The third one is of course by Brahmagupta, the modification of the conical gnomon. And then some later additions were made by Lalla, Shripati and Bhaskara too. And they were actually made in such a way that the diameter is 6 by pi. So they were graduated on the circumference. And the height was of course 12 angulas, and the material was either timber or ivory. So this is just a tabular format. So a gnomon is basically, you can summarize it, that is an instrument which is used for determining the shadows. And now we are going to see the actual working of the Shankhu Yantra. So now this is a very famous method called as Indian circle method, and this method is used to determine the directions. Okay, so in order to determine the cardinal directions, this method is used. So in this method, the Indian circle method, this was first proposed by in Katyayana Sulba Sutra. So it is another text of Indian astronomy. Rather, not Indian astronomy, it belongs to Indian literature, not exactly astronomy. So this Indian circle method, as you can see, what you have to do is take any one of the three types of gnomon. So I have considered the rod, the third type of the gnomon, as proposed by Aryabhatta. So in the center, you can see OG is the gnomon, and the procedure is as follows. What you have to do is create a circle on the ground. Make sure that the ground is exactly horizontal. There should not be any, you can say, variations in the horizontality of the ground. Make sure that the ground is level and uniform. Now what you have to do is construct a circle in such a way that the radius of the circle is equal to the height of this gnomon. Now what you can do is place the gnomon at the center of the circle. So you can see at the center is point O, and there is where you have to place it. Now there is a method to obtain the shadows. So you can see point P, and you can see the sun above. If you extend the line from PG upwards, you will see that it intersects with the sun. So now when the sun is rising from the eastern direction, it is going to cast a shadow on the western side. So we have to take an observation before the noon and mark it with point P. So the point P is actually the shadow of the tip of the gnomon, which is intersecting the circle which you have constructed. So mark it with point P. Afternoon, so noon is exactly midday, that is 12 p.m. today. And afternoon is considered to be after 12 p.m. before noon is considered to be before 12 p.m. So you have made the first mark before noon or in the forenoon, which is point P. Repeat the procedure after noon, after 12 p.m. in the same time interval, and mark the point as P dash. So now what you have is, you can say, the tip of the you can say the tip of the gnomon is casting a shadow on the circle, and you're making markings of that shadow. Then simply join P and P dash. Once you join P and P dash with a straight line, now what you have to do is construct a perpendicular bisector of P and P dash. So perpendicular bisector basically divides P and P dash into two parts at 90 degrees angle. So when you construct the 90 degrees or perpendicular bisector, that is the north-south line. So this line will tell you where is north and where is south. And the perpendicular bisector of the north-south line will finally give you the east-west line. And by using this simple method of simply shadows and plotting the markings before and after the noon, you can find out the cardinal directions. So this method was used even in 3000 BC, before Common Era, because it is a really simple method. But the thing is, there is an error in this method. So if you might have noticed, this method assumes that the sun rises exactly at the east and sets exactly into the west. But that is not the case. This happens only at the equator on vernal equinoxes. This is not always the case. Sun does not always rise in the east, it does not always set in the west. It rises somewhat to the south or somewhat to the north, which we refer to as Uttarayan and Dakshinayan respectively. So the thing is, this method does not take into account the declination of the sun. So you remember from positional astronomy lecture of Dr. Sagar Gokhale, we discussed about right ascension and declination. So declination is basically the distance, angular distance from celestial equator. So in order to define a celestial equator, what you do is, suppose this direction is the north-south, and this line joining the north-south direction is called as the meridian. Perpendicular to it will be the celestial equator. So imagine there is a semicircle over here, and that is the celestial equator. So declination is how far you are from that celestial equator towards the north or towards the south. So that is declination. So the sun is sometimes going to rise from southeast and set into southwest, or sometimes the sun is going to rise from northeast and set into northwest, and this method does not take that into account. So this is an error of this method, and this needs to be rectified. So there's a second method which was proposed by Brahmagupta and the later astronomers Lalla and Shripati. So this method considers the declination of the sun. So when you try to find out about the declination, you see the figure on the right and you see a formula at the bottom. So I'll just explain what that formula is. You repeat the same procedure, only in this way you are looking at the figure from the top. In the initial, you can say, in the initial slide, you were looking at it from the bird view. So now you have to imagine you are looking at it from top. So O is where the point O is where your Shankhu Yantra is, the gnomon, and it is coming out of the screen or going into the screen. Then we have north, south, east, west, which we have determined from the earlier method. But now you can see the P and P dash line. It is slightly inclined. It is not exactly horizontal or parallel to the east-west line. It is slightly inclined, and that is because it has not considered the declination of the sun. So now on the left-hand side, you can see the formula. So I'll not explain exactly the formula because it is too much into spherical trigonometry. When you get the notes, the formula will be explained. I'll just explain the definition of that thing. So X is actually the corrected amount considering the sun's declination. The corrected amount considering the sun's declination. That is X. In the figure, X is equal to PQ. So there's a very small distance. You can see P and Q join a line. That is the correction that you want to achieve. That correction is achieved by this formula, where H represents the hypotenuse. So now your gnomon is exactly vertical. It is going to cast a shadow horizontally. And that's going to be a hypotenuse because it is a right angled triangle. So H is actually the length of the hypotenuse. You have to multiply it by the radius of the circle which you have constructed earlier, which is there in the figure right now. And then delta 1 and delta 2 are the angles of the declination. So when your sun is rising, it is not exactly rising from the east. It is somewhat far away from the east. So this distance, this angle that the sun is forming, that is the declination with the celestial equator. So that is delta 1 minus, we have to consider a second observation because you have to consider that gap, that correction needs to be rectified. So r sine delta 1 minus r sine delta 2 divided by r cos of phi. So the phi is actually the observer's latitude. So it is going to change with latitude. So if you consider this in my inclined hand to be the axis of the earth, you have three circles. The equator is the great circle, 23.5, and 23.5 you have the tropics. Okay, so on winter solstice, on the tropic above the equator, the sun is going to be exactly overhead on summer solstice, whereas the sun is going to be exactly overhead on the tropic below the equator on winter solstice. So only on those days the sun will rise exactly at east and exactly at west on the tropics, not on the other days. Similarly, on the equator, the sun will rise exactly on the east and set exactly into west on equinoxes. So that is why this correction is required. Without this correction, your observations are going to be flawed and there are going to be certain errors. So this is the correction proposed by Brahmagupta and this is the formula. Now there's another method called as the three shadow method. And this is a kind of funny method because it takes into consideration bisectors. So now how does this method work? So again, you have to construct a gnomon, a straight gnomon, plant it into the ground. Now what you have to do is make three marks. So the line at the center is the shadow cast by the gnomon at the midday, which is the 12 noon. So a mark before it slightly, and with the equal time interval after the midday, that is the third mark. So when you have drawn three lines, which are actually the shadows cast by the gnomon at three different times, now what you have to do is construct two fish-like figures. So that is simple geometry. You construct arcs. So when you construct these two fish-type figures, in order to determine the perpendicular bisector, you have to extend those bisectors and join them at a common point, which is given. That is the center of the locus. And from that point, you have to construct a circle which passes through all these 3 points, that is the tips of these three lines. And that way you will achieve the circle which will actually denote the path of the sun. So you can see the path of the sun is not exactly circular, it is elliptical, and that has an effect even on the shadow caster. So the path or the locus will be somewhat elliptical, and this method can achieve it. So that is why this was a correction proposed by Brahmagupta and Varamira in the later texts. And now what about the directions? The foot of the gnomon and the center of the locus, when you join these 2 points and extend the line, that will be the northern direction. 180 degrees to it, that will be the southern direction, and you have east and west. So this can be used to ascertain the directions with the correction of sun's declination. And this was proposed by Varamira. So these were the types of gnomon and certain additions that were made by the astronomers and mathematicians without and with considering the sun's declination. Now to determine the time. So I'll not get into the derivations of these formulas, but just try to I'm just trying to show you the formulas for how to determine the time. So in the first formula, it was proposed by Brahmagupta. Time is equal to d by 2, where d stands for the day length. So d by 2 is simply half of the day, because only in that time the sun is available to you, from 6 a.m. to 6 p.m. In the denominator, you have 1 plus s by g, where small g is the length of the gnomon, which is generally 12 angulas, and s is the length of the shadow cast by the gnomon at the time which you are considering. Okay, so this is the first formula. Now the thing is, this formula does not give you the accurate time, because again, this formula does not take into consideration the declination. So that is why there was another formula which was given in Yavana Jataka, which is on the right hand side. Yavana Jataka was proposed by Spujidhwaja. And Yavana, if you see the word Yavana, it is derived from the word Ionian, which is actually Greek. So Yavana Jataka is actually a translation of Greek astronomy into Sanskrit. And this formula is given in Yavana Jataka. So now if you try to see, you have the gnomon length and the half day length in the numerator. And in the denominator, there is an extra term which has been added, which is S dash, or S prime you can call it. So S prime is actually the shadow of the gnomon at midday. Okay, normal S is just the shadow of the gnomon at that time, but S dash is particularly the shadow of the day or you can say the shadow at the midday, at the afternoon, 12 p.m. Then we have the third thing, equation of time as given by Varahamihira, and he introduces a concept called as Nadika. So Nadikas are actually a unit of time which defines 24 minutes. It is also called Ghatika sometimes. So we have Nadika, which is 24 minutes, and you have the formula for that. So in that formula, he is considering zodiacal signs as well. So when the sun is moving along the ecliptic, the zodiacal signs are also moving because the earth is rotating from west to east. So we see everything rising from the east and setting into west. So this formula also gives you how many rashis have elapsed since the daytime. So this is a really good formula, and on the right hand side you have the method to obtain lagna. Now try to understand, lagna is actually the intersection. That is what lagna means, or you can say conjunction, a joining. So lagna is calculated by Varahamihira, and you can see the term L, which has been added. So that is actually the longitude of the sun, okay, celestial longitude of the sun. So this is in general how you can determine time by using the gnomon. And these are the formulas which are proposed by various astronomers and mathematicians from different texts. Now this is another type of gnomon called as horizontal gnomon. So right now we were dealing with vertical gnomon. What if you place the gnomon horizontally and you attach it to a vertical object? And that is exactly what is done here. And there is a shlok in the left side of the image, and below that is the literal translation. You can refer to the translation if you want. I'll just explain the figure. So when you're looking at the figure, there are two terms which have been mentioned: zenith distance and altitude. So the altitude is really easy to measure. What exactly is altitude? So when you're looking at the north and when you're moving towards the east, the angle that you're tracing along the horizon, that is called as azimuth angle. Okay, so suppose you want to plot a star in the sky. The first step to plot the coordinates of that star is look towards the north, start moving towards the east. Suppose here is the north and I'm moving towards the east. That angle is called as azimuth angle. And when you move up into the sky towards the star, that is called as altitude. So when the sun is rising and it is reaching at a certain point in the sky, you can determine the altitude of the sun from the horizon, and it is forming an angle with the ground. So if you try to see, I'll check if my pointer is visible. Yeah. So the line joining the, oh sorry. So when you are seeing the sun, there is a straight line which is intersecting the ground. It is forming an angle with the ground which is called as altitude. And it is forming another angle with the vertical, and that angle is actually the zenith distance. So now what exactly is zenith distance? So zenith is actually the highest point in the sky. It is called as Khaswastik. Okay, it lies on the meridian, and meridian is the line which joins the north to the south. And this point is the highest point in the sky, and it lies on the meridian. And from that meridian, how much far away the sun is, that distance is called as the zenith distance. And even the zenith distance is creating an angle with the vertical. And if you simply consider, it is just a matter of vertically opposite angles. They are going to form equal angles in this triangle, the triangle below it. So the gnomon, which is placed horizontally, and the sun ray entering from this side, it is going to cast a shadow on that vertical support. And that vertical support is actually graduated. So the shadow will determine what time of the day it is. So the closer the shadow is, the closer the sun is to the zenith. So which means it is closer to noon. And that is how it will be determined. So now there is a simple formula given below. It is simply a ratio of hypotenuse, shadow, and the gnomon length. So these are simply mathematical terms which can be easily derived from trigonometry. Okay, just take into note that A, which is given in the formula above, that is the R sine of the altitude of the sun. Now altitude is the angle. Altitude is not the distance. We have to take this distance. So that is the R sine. You can simply apply trigonometry. You will get R sine of the altitude of the sun. Similarly, you have Z, which is the R sine of the zenith distance of the sun. Again, apply trigonometry at the upper triangle. So zenith distance is again an angle. We don't want the angle, we want the distance. And that distance is taken as the R sine of that angle. And that is what they have given at the bottom. So this is another method which is also used in sundials, and this method is used in Jantar Mantar observatories which were built by Savai Jai Singh. And this is an equatorial sundial which has been used in Jantar Mantar. And here lies the principle, the horizontal gnomon. So this is about everything about gnomon. So gnomon, all it deals with is a simple stick or a rod or a cylinder or or a conical object of which the shadow is cast, and we find out from the shadows the directions and the time. So the next yantra literally means chaya yantra, which means the shadow instrument. So now there are two figures, and these are a really interesting concepts. So these two figures are actually going to tell us the diurnal motion of the sun. So what is diurnal? Diurnal simply means the daily motion of the sun. So as I said earlier, the sun doesn't always rise in the east and set into west. It rises somewhat to the north or somewhat to the south. So the circle that it traces in the sky for that day is called as diurnal circle. It is simply the path of the sun in the sky for that day. Diurnal circle changes every day. So we have to plot the diurnal circle every day, and that is exactly what this yantra does, Chaya yantra, the shadow instrument. So let's try to focus on the left hand side. And the procedure is as follows. You consider a level circle as described earlier. Take a gnomon. Gnomon is placed at the center, which is point O. Construct a circle in such a way that the radius of that circle is equal to the height of the gnomon. Now what you have to do is observe where the sun is rising. So the sun, if it is rising slightly away from the east, it is going to have an angle. And that angle is called as agra. So agra is basically how far from the cardinal east the sun is rising. So it is not exactly at east, it is somewhat either to the north or to the south. And that is what you are going to note. So the first observation is plotting point A, as you can see in the figure. So A represents the sun's rising point and E represents the exact east. So even in the figure, you can see that the sun is not exactly rising from E, it is rising from A, which means there is some kind of agra. When the sun is rising from A, you have to note that you have to take that observation, and simultaneously when the sun will be setting, you have to note the setting point as well. So that will be A and B. A will be the rising point, B will be the setting point, and they will give you agra. So segments GB and EA are actually the agra which has been obtained. Now what you can do is, by using these figures, you can construct another circle. Okay, so join BA, which you have plotted earlier by a straight line. The line AB intersects north-south line at point C. Place your you can say the instrument at point C and construct another circle. Part of it is dotted. So that circle is we have to consider, circle ADB. And that circle will actually give you the diurnal circle of that day. That circle will determine how the sun is going to move for entire day. And this is a method to plot that diurnal circle so that we can determine the declination. When you keep on repeating these experiments every day, you see how the sun is moving either towards the north or to the south. So on the left hand side, you can see that it is a position of Uttarayan because the sun is rising towards northeast and setting towards northwest. So it is a position of Uttarayan. On the right hand side, you can see that it is a position of Dakshinayan because the diurnal circle has shifted to the left towards the south. So it is the position of Dakshinayan. Whereas on the right hand side, it is the position of Uttarayan. So this was a method called as Chaya Yantra, which was used to determine the declination and the diurnal circle, the daily circle. But there were certain improvements which were done by Lalla and Shripati, because the earlier image which we saw, there is a certain, you can say, in geometry, the diurnal circle should not go outside your level circle. So in the earlier figure, it is actually going outside the level circle in figure B, and that is not how it's supposed to be. So this is how Lalla and Shripati actually proposed it. It is essentially the same concept, only the difference is now the diurnal circle is lying exactly inside the level circle. And now you can actually visualize how it works. So the dotted line above is the daily motion of the sun, the diurnal motion of that day. It has been projected to the plane of the equator. Okay, and that circle which we have defined, A, D, B, that is the path of the sun of that day. You have to do this every day. So now the thing is, you must have questioned, why exactly would Indian astronomers actually know this concept of declination? How did they come to know that the sun doesn't always rise in the east and always set in the west? So we have heard of a concept called as Arghya. So there are many stories in which our characters wake up in the early morning and give Arghya to Surya. And that is actually a part of observation. You give Arghya to Surya every day, and you are going to notice that the sun is not rising exactly in the same location every day. It rises on different points. So suppose there is a river, and let's say, for example, a character called Karna is given Arghya every day to Surya. And the sun today is rising exactly behind the tree. So the disk of the sun is behind the tree, and the tree is exactly in the center. When Karna is giving Arghya every day of the year, he will notice a shift in that disk. And that shift is because of Uttarayan and Dakshinayan. And this is how they came to know about the concept of declination. And the root origin of this is actually the concept of Arghya. It is just everyday observation of the sun. It has got nothing to do with the ritual or the tradition. It is just an observation of the sun. And by using these observations, the later Indian astronomers developed all these concepts. So the next is Yashti Yantra. So in earlier slide, we saw Namon is plotted vertically and the shadow is cast and we see a hypotenuse, a right angle triangle. So in this yantra, the Yashti yantra, we have to plot the instrument inclined manner. In this manner. So now we are trying to imagine a hemisphere. So you're sitting on the ground and there's a hemisphere over top of you. And in that hemisphere, you are placing the gnomon. So this is basically a gnomon, but it is the form of a Yashti. Yashti basically means hypotenuse. So OA is your instrument, which is placed in an inclined manner to the horizontal, and it is looking towards the sun. So let's say the sun is rising in the sky, it is at a certain position in the sky, and your Yashti is pointing exactly towards the sun. So it is going to form an angle with the ground, as we discussed earlier. That angle is called as altitude. And then it is going to form another angle with the meridian. That angle is called as the zenith distance, which we discussed earlier. So in the figure, zeta is the angle of the zenith distance, and A is the angle or rather A is the altitude of the sun. And we have to take the sine ratios. So we have to take OB and OA. And that will help us to plot again the diurnal circle. So on the left hand side is given the shlok of how to construct a Yashti Yantra. It is simply trigonometry. All you have to do is draw a circle, place a Yashti Yantra at the center, and point it towards the sun at a particular position. And that will give you how the sun is going to move in the sky. So this is just, you can say, a modification of the earlier version. So on the left hand side figure, you can see that at the center is O, and OA is actually your yantra, which is simply a gnomon. And now it is pointing towards the sun. So when you extend OA, it is pointing towards the sun. And when you try to see that point, B is where the sun was rising. So when you note the point B, you can see it is away from E. So again, you have to consider the declination. It is not rising exactly at the east. Sun is rising slightly away from the east. So that point is B. The sun is rising from the point B. It is moving up in altitude. And finally, at a certain position, you are trying to plot all of the diurnal circle. So consider at A. When you extend OA to the sun, you are going to get a line and you are going to get an arc. So that arc is OB. And if you extend that arc in a semicircular manner until it intersects with the point B dash, which is actually the setting point of the sun, which is again away from the west side. So because this is the position of Uttarayan, the sun is rising from northeast and setting into northwest. But this yantra can help you determine how the sun is moving and what time of the day it is. Because the circle that you have constructed, this arc that you have constructed, is actually graduated in ghatikas. So you can achieve an accuracy of up to 2 seconds by using this yantra. So the accuracy is very high by using Yashti yantra. And it has been used in Jantar Mantar again. So this is the basic concept, and on the right hand side you can see the literal translation of the verse, and that is taken by Brahmagupta. Now this can also be used to plot the direction. Now as we saw earlier, we already know the east-west direction. But this method can help us to determine the diurnal circle and how far away you are, or rather what is your latitude. And Yashti Yantra can help you to determine your latitude as well by knowing the declination. Because you have just plotted the diurnal circle and you can see that the EW line, if you imagine the EW arc which is visible in the figure, and the another arc which is the diurnal circle, there is some distance between them. That declination can help you to determine the latitude of the place on which you are taking the observation. So this can also help you to determine the directions as well as your latitude. Now this is a side, you can say this is slightly a different figure, and this is in connection with spherics. So spherical trigonometry is really difficult, but it is used in Indian astronomy as well as all other types of astronomy. So on the left hand side, you're looking at the entire celestial sphere, which you should imagine in this way. You can see the north and south. You can see the east and west. Z represents the zenith, which is the highest point in the sky. Okay, Z is the zenith. The upper hemisphere and the lower hemisphere are separated by the horizon. So just imagine you're sitting and you have the horizon in front of you, highest point in the sky, north and south, east and west. That is exactly what the figure is. And now you start taking the reading. So the sun is rising, and let us assume that the sun is at position X as seen in the figure. OX is exactly your Yashti, which is looking towards the sun. From OX, you can find out the altitude again, and you can find out the zenith distance. So zenith distance is nothing but the arc XZ. That is the zenith distance. And altitude is simply OX and the arc that it subtends. Okay. Now what you have to do is consider the trigonometry, simple trigonometry. OX is the sine ratio of the angle XOA. Again, XOA, that is the angle, which is the altitude. Opposite to that is the side XA, which is the projection, and that is what we need. So XA can be found by simple trigonometry from the angle of latitude. OA can be found out by the zenith distance, which is angle AXO. So this we have learned in 8th standard, simple trigonometry. So we have found out XA, we have found out AO, and there are terms denoting this as well. So XO means Yashti, XA means Shanku, and AO means Drugja. So these three terms have been defined as per Indian astronomy. Now if you can observe in the figure, once again, there is certain declination. The sun is not rising exactly at east, it is rising at a point which is labeled E dash, away from the east. It is rising from east and setting all the way to the west, but not exactly at west, north of west. So there is again a certain declination, and this is the position of Uttarayan again. And that is why those arcs have been given, so that you can analyze them and imagine them easily. Now what you have to do is find out the distance of A and C, point A and point C. That is the distance which you need to find. So the distance of the foot of your gnomon up to the diurnal circle, that is what we are going to find. And that is again really easy. Consider triangle AOB. It is a right angled triangle. It is right angled at OBA. So if it is right angled at OBA, I can show you the figure actually. If it is right angled at OBA, so you can see at this point there is going to be a right angle, so opposite to it will be the hypotenuse. Then we have a bhuja, and then we have a koti. So on the right hand side of the image, they have given a formula, and you can easily recognize that formula. It is actually Pythagoras theorem. But this method is different from what Pythagoras used. And this was proposed not just by Brahmagupta, not just by Aryabhata, but this formula is also present in Baudhayana Sutra. So Baudhayana is actually a guy who proposed the Pythagoras theorem even before Pythagoras. And he used the method of spherics exactly by this method. So it is given at the bottom. Koti is equal to root of Drugja square, which we calculated earlier, minus Bhuja square. And this is again, as you can see, this is literally the definition of Pythagoras theorem. And above it, you see another formula which says Bhuja is equal to Shankutala plus Agra. Shankutala is AC and Agra is how far away it is from the equator. So if it is Uttarayan, BC will be added, and if it is Dakshinayan, BC will be subtracted because it will be towards the south. Okay, so that is why the sign plus minus. And this is what Yashti Yantra is all about. This is slightly accurate than the Gnomon or the Shanku Yantra. So the next one is Shalaka Yantra, a needle instrument. So now this is a really simple method proposed by Lalla, Shalaka. So what you do is take a horizontal stick or a horizontal rod of length AB. Generally, it is considered to be of 12 angulas. 12 angulas is considered to be a standard unit. You place AB horizontally, and then you take another vertical needle. By the way, the length of the needle is not yet defined. We have to define it. So now you take another needle and place it in such a way that if you look through point C, your vision, or the, let's say, the ray of light should exactly intersect with the star which is going to rise. Okay, so that rise of the star will tell you the amplitude, or rather the agra. Agra means how far away from the east that star is rising. Okay, and this method and this yantra can easily help you to examine, or rather determine, the agra of any star or any planet, or even the sun, or even the moon. And this is a very simple method proposed by Lalla. And once you have achieved that thing, you can fix the length of the needle. The length of the needle is AC. So this is actually, you can say, a recurring thing, because you have to keep on adjusting this length. So the needle can be mounted on top of it, another needle on top of it. Depending on your observation, it will help you to determine the agra. And this was proposed by Lalla. This is called Shalaka Yantra, the needle instrument. There is another type called as Shakata Yantra. So Shakata simply means the card, or you can say a V kind of thing. So there is another form called as Shakata Yantra, the card instrument. And if you can see in the figure, on the left hand side, there is no need to read the shlok or the literal translation. I'll explain what is happening here. The Shakata Yantra is literally a V. So there are two nodes which are joined at the center, and from their tips, plumb lines are suspended on the circle below. So those plumb lines will be moving according to the angle between what you are measuring. So this Yashti Yantra, Shakata Yantra, it is a type of Yashti Yantra, can be easily used to determine what tithi of the day it is. Okay, so I'm not sure if the tithi will be covered in Graha Ganita, but just to give you a rough idea of what a tithi is simply a lunar day. Divasa is a solar day, whereas tithi is a lunar day, and there is a variation in them. So Divasa is actually measured from sunrise to sunrise. Tithi is not measured in the same manner. So how is exactly a tithi measured? So our calendar system has two types, Amavasyanta and Purnimanta. So in the Amavasyanta system, our calendar starts with an Amavasya and ends in Amavasya. So when the calendar starts with Amavasya, the angle, or the north, south and east-west distance between between sun and the moon is 0. So the term Ama Vasa literally means moving together. Ama means together and Vasa means moving. So at Amavasya, moon and sun are actually together in the sky, which is why we cannot see the moon. From Amavas, the first night after Amavasya, the moon has moved forward by 12 degrees. This measure of 12 degree is what a tithi is. Okay, it is basically the gain of moon on the sun by 12 degrees on ecliptic longitude. I'll repeat once again. Tithi is the gain of moon on the sun by 12 degrees on the ecliptic longitude. So that is what a tithi is. So after Amavasya, the first tithi, the first step, which is of 12 degrees, is Pratipada. So by using this instrument, you can easily measure it. One of the instrument should point towards the sun. I mean, the one half of the instrument should be towards the sun. The second half should be towards the moon. So if it is Pratipada, the angle that will be subtended will be 12 degrees. So this angle can easily be measured on the circle below. So simply by seeing the circle and the shadow that it casts, you will realize what tithi it is. If the angle is 12 degree, it is Pratipada. If it is 24 degree, it is Vidya, and so on. Just the table of 12 up to Purnima, when the angle will be exactly 180 degree, and this will be exactly straight. Okay, and similarly the process will continue in Krishna Paksha. So this is used to determine the tithi, rather the elapsed tithi or the running tithi. But this does not measure, or this does not tell you why the tithi is repeated or why the tithi is omitted. So why does the tithi vriddhi happen, or why does the tithi shaya happen, is not measured by this instrument. This can only give you the running tithi of the day. It cannot give you a tithi vriddhi, or it cannot help you measure a tithi kshaya. Okay, this is a simple instrument called as, based on spherics, called as Shakata Yantra, because it looks like a Shakata. Then we have a Chakra Yantra. So chakra yantra is also present at Jantar Mantar. So this is the chakra yantra proposed by Aryabhatta. So on the left hand side, you can see that there is a ring which has been made. So Aryabhatta, now you can actually read the paragraph on the right hand side because this shows the method of construction. A chakra yantra bears on its circumference 360 marks of degrees and two holes are made. So I can see in the figure A there are two holes, and these two holes are placed in such a way that the ring can move. So suppose the ring is like this, it should move in the vertical axis. So the step one is that the hole above should look at the sun. So arrange it in such a way that the sun rays pass to the first hole, and then move it in such a way that they even pass through the second hole. So that is what is shown in the figure on the left. You can see a straight line passing through both of these holes. So that will help you to determine from where the sun is rising. If you know from where the sun is rising, you can find the agra, and depending on what position, you can find the altitude and the zenith distance, and you can immediately find the time of the day on the level circle below. So this is a chakra yantra which has a chakra of rotating, or you can say it keeps on rotating depending on how the sun is moving. So there is another modification proposed by Aryabhatta himself, in which he says that it can be suspended by plumb lines on both the sides. So this is just to again ascertain the verticality. So it should not be inclined in any axis. If it is inclined, it will affect the shadow below, and then it will affect the time. Okay, so this is the chakra yantra or the circle instrument. And this is an alternative thing proposed by Varahamira. So it kind of modified it and simplified it. So if you try to see, the chakra has only one hole, and that hole should be focused at the sun. So when you extend the line of the sun, and from the center, when you extend the plumb line, that angle which is getting formed is nothing but the zenith distance, which is the R angle of the sun. So all these attempts are to find the R angle of the sun, because that way we can determine the time of the day, depending on how the sun is moving in the sky. So Varahamira's chakra yantra achieves that in a very simplified fashion by suspending a plumb line, and by aligning the hole with the center, you can achieve that angle, and that will give you the zenith distance. So this was proposed by Lalla and Bhaskara too, by the way. And there is even a formula. So in order to calculate the time of the day, that is simply is equal to semi-duration of the day, which means d by 2. Semi-duration simply means half the duration of the day, from 6 a.m. to 6 p.m. Because 6 a.m. is considered to be standard sunrise and 6 p.m. is considered to be standard sunset, into sun's altitude. So depending on at what position you are taking the observation, the altitude is going to change, and hence the time will change, divided by the sun's meridian altitude. So as I said earlier, the meridian is a line joining the north and the south, and depending on that position, you have to calculate the sun's meridian altitude. Okay, that will give you the time of the day, and this yantra can help you determine it because it directly measures the altitude, and you can find the half duration of the day. Then we have a Dhanur yantra. So yeah, the next one is Aryabhatta's Dhanur yantra. So as the name suggests, it is a dhanush. Looks like a dhanush. It is a semicircle instrument. So what you have to do is start by aligning the instrument in the east-west direction, or rather with the sun's rising point. Okay, so this instrument will not be in this manner. It will be slightly in the east-west direction. That will help you to determine the declination. After that, when the sun starts rising and you have to take the actual observation, you have to move it towards the north or the south respectively. So that will help you to determine the azimuth angle. So now remember, azimuth angle is actually measured from the northern direction, but here our instrument is moving and not the sky. So that is why we are moving from east to west. Okay. So when the Dhanur yantra is moved, there is another you can say a small object which is suspended on it, which is labeled as C, and that C moves over the surface of the dhanush, and that dhanush is marked with gradations, and those graduations are along the circumference, and they have the ghatikas. Okay, so depending on where the shadow of that C is going to fall, that will help you to determine what time of the day it is. So in the figure exactly, when the sun is at the given position, its shadow is falling on the gnomon, and it is, you can say, it is suspending downwards and forming a mark. But at where it cuts the dhanusha, there is a ghatika, or there is a mark of a ghatika, and that helps you determine what time of the day it is. The only condition is you should set it properly towards the rising point of the sun initially. If you lose that reference, your yantra is going to completely fail. Okay, so this is how it works. And this is another variation proposed by Lalla. Okay, so this is again a simple thing. It is a semicircle instrument. At the center there is a needle, and the needle casts a shadow. So when the sun is at a particular position, the sun rays are hitting the needle. The needle is casting a shadow at the bottom, which is denoted by point F. The arc CF is nothing but the altitude of the sun. Similarly, you can even determine the zenith distance. Once you have determined the zenith distance and the altitude, you have the diurnal circle, and you have everything about how the sun moves for the day. And then you can determine the time. So on the right hand side, there is a translation given which helps you to determine the nadis that are left behind or that are elapsed or that are coming, depending on when you are taking the observation. So if you are taking the observation before noon, it will tell you how many tithis have elapsed. If you are taking it in the afternoon, they will tell you how many tithis are remaining for the day. The next is Bhagana or Nadiwala Yantra. This is also present in Jantar Mantar. So actually, instead of referring to this figure, I'll show you the image later, which is going to occur in the PPT. So just remember, you're looking at it from the top. You have east and the west direction. O is where the gnomon is. When the sun rises at that point, you have to extend that line on the circle. That will give you a first mark, which is denoted by A. And then as the sun is moving to trace its diurnal circle, it will, you can say, simultaneously trace an angle below. So the arc AB that it is tracing is actually how the sun is moving in the sky. So because of that motion, it is tracing an angle, and that circle is graduated. Okay, so suppose arc AB shows 3 Ghatikas. So you can imagine that this shows the time of the day in Ghatika, but it is like a huge clock. Only the difference is this clock works on shadows and not time and minute hand. So this is Nadiwala Yantra, and this is also there in Jantar Mantar. It is inclined by the latitude of the place. Okay. Then we have Pitha Yantra, the literally seed instrument. So it is, if you even look at the figure, you can easily determine that there is a base. So the base is graduated in degrees, 360 degrees, and there is a gnomon at the center, and it is going to cast a shadow, and that will literally give you the time of the day. So this instrument came much later. However, this instrument does not take into consideration the declination of the sun. So this is a lesser accurate instrument, but still it can help you to determine the time, which is why there is a method which is used to determine the corrected time. So this does not give you the exact time, which is why you have to apply a correction, and that is given in the formula below. So the corrected time is observed time, which is taken from this instrument, into length of the daytime divided by 30. So 30, regarding this experiment, Shripati has not really given a method. So there are many of the ancient Indian texts where you directly have the results, but there is no procedure given for them. The procedure is lacking. There is no recipe. There is directly the result. Okay. So similarly, Shripati has not really given the procedure. He has directly said that you have to divide it by 30, because maybe that is the number that he has arrived from as a dimensional constant. Okay. But there is no method given in there. You can search for it, but definitely in this Siddhanta which I read, there was no procedure given for it. This is one of the most famous instruments, which is called as Ghatika Patra. So it is a part of water instrument or a clepsydra. So these are the 3 types of water instruments that were used in many of the ancient civilization. Type A is called as outflow, right? Okay. Type B is called as the suspended type, because there is a bowl at the top and there is another bowl filled with water, and the second bowl keeps on emptying. Okay. And depending on the rate at which it flows, it will help you to determine time. And the third one is inflow. So the water is flowing inside the cylindrical container. So out of which in ancient India, type A was used. And this is how the Ghatika Patra looks. So this has been adapted from a book called Measurement of Time, written by Shri Deepak Joshi. If you see the figure on the left, this is how it exactly the Patra looks. And you can find this Patra is used even today in the marriage ceremonies or the threading ceremonies of Hindu, or you can say in the Hindu ceremonies. So Ghatika Patra actually helps you to count the Ghatikas. So when this Patra is emptied twice, it is going to measure 1 Muhurta. When it is emptied once, it is going to measure a Ghatika, which is given in the conversion table on the right hand side. Muhurta is simply 48 minutes. That is all it is. There is nothing you can say astrological about a Muhurta. Muhurta simply measures a time period of 48 minutes. Okay. and Ghatika measures a time period of 24 minutes. And this can help you to determine the ritual or the time of the ritual. So, since in the ancient times, Vedic rituals were considered to be of utmost importance, they were yajnas. So, in order to determine the time of the yajna, there had to be certain instrument which could help you to count the time, and that was Ghatika Patra. So, it is really a really ancient instrument. There is a you can say a man by the name of David Pingree, and he has done many translation. And he has, however, proposed that this water clock actually came from Babylonia into India. But then again, Yukio Ohashi did further research and he found that these Ghatika Patras are actually present or they have been excavated at the sites of Mohenjo-daro in Indus Valley civilization. So it might be possible that the concept of Ghatika Patra or the water clock transferred from India to Babylonia in the ancient time, and then during the Persian invasion, it got traveled back to India again. And that is possibly what David Pingree is referring to. But this was present in ancient India, and the references can be found in all of our Shruti texts. There are certain miscellaneous yantras. So this is actually a calendar stone which was found at Mohenjo-daro. So Mohenjo-daro is a civilization which ranges as back as 3500 BC. So they had to determine winter solstice and summer solstice because winter was very harsh for survival, whereas summer was easier for harvesting. So in order to determine winter solstice and summer solstice, when does the winter season begin, when does the summer season begin, they had created a stone. Now the thing is, this is still the mystery of the stone is still under exploration. Nobody has tried to figure it out how exactly does it work because there are no records for this calendar stone. There are certain you can say the research is being done about this calendar stone, but no exact conclusion has been achieved or no exact conclusion about the procedure of this instrument has been achieved. But this is definitely a stone which measures time or basically a calendar. So this is another thing. So if you see in the figure on the left, it is actually the photo of that place. It is slightly inclined, okay, because that is pointing towards the North Star, which is again the latitude of the place. Because how the altitude of the North Star, it's simply the latitude of your place. So on the left hand side, you can see that it is slightly tilted or above the ground because it is pointing towards the North Star. And this is again like a calendar thing which points towards the north, which shows you how the stars are moving. And on the figure below it, you can see that they have plotted the various locations of the stars, the directions, as well as the solstice positions and the equinox positions. So this was again not an instrument actually. This was a method which was used in ancient India during the time of Indus Valley civilization. Yeah, so coming to Jantar Mantar observatories. Jantar Mantar observatories were built by Savai Jai Singh, Maharaj Savai Jai Singh II, and he has built 5 observatories in total. So out of which these are some of the instruments which are found there. So the first one is Kapala Yantra. So if you see, it is like a huge hemispherical bowl, and that bowl has 2 strings which are perpendicular to each other, and that string has a blob at the center, and that blob is going to cast a shadow. And on that hemispherical bowl we can see the inscriptions of Rashis. So when the sun is going to fall on the blob, I mean the sun rays are going to fall on the blob, and the blob is going to cast a shadow, the place where it casts a shadow, that will help you to determine what Rashi the sun is in. So this is actually used to determine the Rashi and the progression of the entire zodiac cycle. Then we have Nadivala Yantra. So you saw this instrument earlier. There was a figure of it, but now you can easily see how it actually looks. So it is inclined, and there is a needle at the center, and that needle is going to cast a shadow over the circle, and the circle is graduated in degrees. Okay, and this half of the instrument can only work for 6 months. For the rest of the 6 months, this half won't work. So you will have to move to the other half of the instrument, which is on that side. That is because of Uttarayan and Dakshinayan. Because the sun doesn't always again exactly rise at east and set at west. It sometimes rises from northeast, in which case this half will be considered. When it rises from southeast, that half will be considered. So this is active only for 6 months. One part of it will be active for 6 months while the other is inactive, and vice versa. So the tilt actually represents the latitude of your place. And then we have Samrat Yantra. So this is a really famous yantra. So if you try to see, there is an incline. So that incline is called as Yashti or the hypotenuse. Then the vertical thing or the huge building that you're seeing in front of you, that is actually kind of a noma. So it is Shanku, and you have the base. Okay, and then there is a semicircular arc which is present. So let us imagine, rather you can see in the figure, that slope is tilted towards the north pole. So that will help you to adjust the latitude of the place. And if the sun is from the eastern direction, the sun rays are going to fall on the slope, and they're going to cast a shadow on that. You can see the semicircular beam, right? So it is going to cast a shadow on that semicircular beam, and that beam is again graduated into degrees. That beam is graduated into minutes, and it is also graduated into seconds. So by using this Samrat yantra, you can accurately determine the time up to 2 seconds of accuracy. Okay, so this is how great this yantra is. Only the thing is, it is really huge. And this yantra is called as Samrat yantra or equinoctial sundial. There are different types of sundial, and this is one of them. And then we have Chakra yantra, which we saw earlier. So this is the actual image from Jantar Mantar, the Chakra yantra. So you can see there are two holes, and there is a center, a beam which is there, and from that beam you have to look at the sun, and that will give you the latitude of the place, that will give you the longitude of the sun, the zenith distance, as well as the agra. And this is yet another instrument at Jantar Mantar. So this is basically a derivative of alt azimuth coordinate system. So you can see the cylinders, and you can see some vertical pillars, and then you can see some horizontal stretches, and at the center you have a cylindrical noma. So when the sun is too much near to the meridian, it is going to cast a shorter shadow which will fall on the horizontal side. Whereas when the sun is lower in the sky, it is going to cast a shadow on the vertical side. And depending on how far away it is, it will give you the azimuth angle as well as it will give you the altitude. So this is simply, you can say, a graphical representation in the 3D format of alt azimuth system. This is how you can determine the altitude and azimuth, the location of the sun as it keeps on changing. And those pillars are graduated with degrees again. So it can also help you to determine the time of the day. And this is again present at Jantar Mantar. So now all of these instruments that I discussed today are not actually, they are not a derivative of my own research. They are derived from the research paper that has been mentioned here, Astronomical Instruments of Classical Siddhantas. It was written by Yukio Ohashi in the Indian Journal of History of Science. So you can refer to this paper, the PDF is available. And in this PDF, all the things that I explained right now have been explained in detail along with analysis and observations as well as tables. So you can refer to this paper, and these are just the credits to that paper. So I hope you found this lecture informative. If you have any doubts, you can definitely ask them and refer to the paper which I've mentioned in the website. I thank all of you for listening so patiently, and a good day.